computer. Right. Okay, so welcome back after that hectic introduction. So last time we were doing some of these recursive descent thingies. The way, let me find where it is. So I think we had, so here's the test we wrote. We have some sample code. We have the scanner written, so we turned it into some tokens. And now we're writing the parser. So we decided to make the expression struct or enum. This is all the types of expressions you can have for this very simplified grammar. So you can see sort of the correspondence here. Keep losing this grammar. So there we go. So we can have a unary expression, which contains a unary operator, which can either be like a minus or an exclamation mark for negation. And you can see that here. These are the two types, followed by another expression. And because it's a recursive type, we have to put it in a box. So that's sort of the basic pattern. There's a few others. So grouping means an expression in parentheses. Binary means one of these binary operators. I think we have, let's see. Yeah, so we just looked over all of the types of binary operators there were. Okay. And then as for how this parse works, you'll notice, so the top level parse calls parse equality, and that's because an expression at the top level can only be an equality. So for each sort of level of the grammar, we have a separate way to parse it. So we started at the top and then at the bottom with the simplest expressions. So a primary, that means something that has no additional structure. Or something that's at sort of the highest level of precedence. So that can be a literal or one of these keywords or a parenthesized other expression. So to parse one of these primary things, you look at the tokens, you look at the first token in your sequence of tokens. If it's a left paren, you try to parse everything up until, or you parse an entire other expression because you've consumed that. Now it's the expression, and then you check the tokens you get out of that to see if there's a right parenthesis. And if so, then you have a valid grouping expression. So you return a grouping containing the expression that you parsed in the middle after the first parenthesis. So, and then the other cases are sort of simple. They are just, they're the literal cases. So there's another worked example. And now we're going to sort of go through the middle steps. So we did primary.
Sorry,
we did
about the parenthesis thing.
Yes.
Why are you only taking out one token? Shouldn't it be like? Oh, wait a second.
Yeah, I can show you. So the sort of the interface we decided to do is you get a reference to a sequence of tokens, and then what you return is if there was a valid expression you could parse out of that sequence, you return that a tuple of the expression that you parsed and the rest of the tokens after the ones that you consumed. So you consume one of the tokens of the original sequence. If it's a left paren, then you know that you could be in a grouping. Then you try to parse another expression.
Oh, it's a new. Okay, okay, yeah, I get it now because that's
So
a
yeah,
new variable there.
you've shadowed
Yeah,
it, right?
yeah.
And then after that, this one could be the right paren if it's a valid grouping. Otherwise, you panic for now. Yeah. All right. So then parse unary, same format. Except this one's not recursive, except when it calls the top level expression. What you basically will see is you pick out the piece that is just like at this level, and then you need to call the appropriate parser for the lower levels. So here, it's a unary expression if and only if the first token is either a minus or a bang. If it is, then you try to parse another unary expression, that's this, out of the rest. Otherwise, you're in this other case where it's a primary.
Let's try to duplicate this a little bit.
Okay.
So if you compare expressions for bank and for minus, you'll see that they're identical. So what we can do, that's one option. We can implement try from trade to make to try to make unary operation from a token, and we just do try from. If it's okay, we get our unary token that we can use directly. If not, we parse it as primary and produce.
Okay. So try from means
try from trade. This guy.
Try from some type, and you'll get a result.
Yep.
And then how about the remaining tokens part?
Well, in both cases, we're looking at the front item. So we take front item and we try to convert that. So it's going to be try from token into unary operator.
Okay. It doesn't have to be try from. Yeah, how about the new sequence of tokens? So it has to be try from a sequence of tokens.
Okay, so if you go to line 50, we get this token T. And this is the token T that we will be converting this try from.
Okay. And then how about the rest? So are you returning? So is that just to handle the minus or bang?
Yes.
Gotcha. Okay. So you would do a try from. You would implement try from for not unary expression, but unary operator, right? Is that what you're saying?
Yes.
Okay, gotcha. Yeah. Okay, I like that. Is there any way to? So the implementation, though, we would still have to explicitly list out all of the types you can be.
We make pattern match on self, and we check two of them and produce corresponding unary operator. Otherwise,
I'm gonna try some melatonin and maybe tug my Johnson. Wish me luck.
Good luck. All right. So you will simple try from token for unary operator.
Unary operator.
Okay. Type error equals whatever.
Can be unit, for example. We don't really care about error here.
Okay. So,
Match on value.
and then, okay. So we had to use, yeah, we had to do that to get all the token types in scope. Minus self. All right, and then it goes. You give a result. Self.
It goes to OK. Self minus, yes.
Yeah, you're right. Okay. Self minus
Just that.
just that. Why did it make parentheses? That's weird. Okay.
Capital S. And this is error unit, yes.
What? Oh, okay. I think is unary operator minus in scope? Because
it shouldn't be.
okay.
You can use underscore here. We don't really care what lifetime it is. Prime underscore.
Thick underscore.
Yes.
That's weirdly specific. Okay. So minus interpreted as a unit variant. Wait, do I have to say like token?
I just use token type, yeah. Yes, token type. Oh, right. It's token type.
Does also need a okay, yeah. Okay.
Underscore.
And now I can probably use token type. So, all right, now it's still going to get confused. I do that. No. All right. Awesome. So now this sort of direct translation is going to be, so we probably have to do this for a few other operator types. That's fine.
Yes.
So match. So if let okay unary equals then try
Unity type.
Operator try from e dot token.
Yep.
Then we will do this. Why didn't I copy? Maybe zoom is messing up. And then here it will be unary.
If you pattern match into operator instead of unary, you can simplify the construction a little bit. So on line 64, replace word unary with operator. Next line. So not okay unary. So go to this okay to the left. So unary. Unary inside okay. Replace it with operator.
Oh yeah, I see what you're saying. Okay.
Yes.
Bye, and now we can do this.
Yep, and we can get rid of all of this.
That's
And we
nice.
can probably drop returns from
true.
both branches.
Okay. Now I think this will only this might work for
Binary operators.
but not all of them. No, because we need something more specific than binary operator here, right? We're parsing out particular kinds of binary operator. So we could either split this out, this enum, or
we can have it in a function. We can have it two different data types. I'm not sure how we're going to use it later.
yeah, that's true. I don't know if does he make a node that's called binary operator, or does he make a node that's called whatever factor comparison, whatever. Let's find out. So he makes something called expr.binary. So he uses binary operator in all cases. He doesn't have specific node types for these different levels.
Okay, in that case, we can make a function called try parse comparison.
Right. Yeah.
Operator try parse binary operator.
Term.
It's probably not term, it's operator and comparison. They will be used in term.
I'll get the names right in a bit. So we have these different functions. Yeah, I don't know. I mean, aren't these sort of the names that we want to use for the categories of operators?
I guess. Well, a comparison, yes. Term, I think better name is sign. If it's
Okay.
positive, negative.
Yeah. Here, I'll name it. I'm going to be just really explicit about what it is. So compare quality plus minus. Small div. I don't know. That's ugly. Can I put this at this level of impl?
I don't think so.
No.
What you can do is to move it one level higher. So outside, then just before semicolon, you add as TT. Cursor left, space, as, space, capital TT. TT token type.
Oh, gotcha.
Capitalize.
Okay, and then just whenever
you should use
here.
that instead. Yeah.
Okay. That's weird. Why can't you do it at the impl level? Just because.
Rust is full of incomplete parts of the language.
Yeah. Kind of sad. All right. All right. So we will get. Okay, I need to sort of compare what our binary let me move this down next to the binary operator stuff.
So why do you have to use the as TT?
Well, it's not a very good idea to import constructors from enum in the first place. It can silently break your code. So if you remove bank constructor, line 131 will turn bank expression will turn into pattern match that assigns it to variable bank. Clippy
Yeah.
will complain that you use capitalized name, but other than that, it will compile. And line 132 will be ignored.
Okay, thanks.
It's for disambiguating. Okay, so the operators we can have in a comparison are greater than, greater, equal, less, less, equal. These. I can't believe that worked. So let's figure this out. So this is TT. Doesn't like that for some reason. Expected. Do I? This it's a new version of Rust thing. All right. Right. Okay. And this is a result. Okay. Now okay, so for equals, we have equal, equal. This is pretty tedious. I can see why people like to use parser generators. All right, I need to say what type error is, or maybe we can, maybe we don't need that.
We don't really need type error, it can be just unit.
Yeah.
It
and this
doesn't
alias
even have
is
to be
this.
result, it can be just option.
Yeah, because we don't care about the error. Yeah. Okay. And then now I need to actually match it. Some, none. Okay. Oh, I never started the live session. Yeah. All right. I'll do that. If anybody wants to troll the code. All right. These will also be some. Plus minus plus. And then this will be star. Yeah, slash star. Okay, we didn't think that was a binary operator. Interesting. Slash star. Okay, there we go. All right, I put this below the crap. So parse factor. Now these are sort of smaller. Let t equals tokens dot get 0. If let sum operator equals binary operator, try parse null div, I think. that token. All right. Okay. So this is the first one. This is the first one where we have a rule that is not actually recursive. It is this sort of star pattern thing. So I think we will need to what is it? Oh, okay. So the first thing we need to do is parse a unary. Parse one unary. Then we try to parse a star or a slash, and then this will be a while. And then
we can still make it recursive, I think.
Didn't they? Okay. So the whole reason that he did this thing is because he wanted to avoid left recursion, but he didn't really say why he wanted to avoid left recursion. So let me see if it says something.
Okay, let's try with while.
Left. Okay. Some parsing text techniques, including the one we're going to use, have trouble with left recursion. Let's see. Each method for parsing grammar rule produces a syntax tree for that rule and returns it to the caller. When the body of the rule contains a non-terminal, call that other rules method. So, okay, he's worried about stack overflows. So if you can't do any tail recursion or anything, if you have a whole bunch of like binary operators chained together, your stack will get deep.
I see. Okay. Let's try to use while.
I'm not super worried about that, to be honest, but I will use this way. So get another unary, and then we need to do this, and then refresh t equals next token. I guess what happens if we and then return. So wait, actually, what's he do to sort of accumulate the? Oh, I see. He's accumulating an entire expression. So at each iteration of the loop, he has to make another binary expression and then sort of add it to the existing one.
A fun fact, once we start creating this recursive structure, drop call for it is going to be recursive, and it can stack overflow as well.
It can't wait. Can it stack overflow even if the original didn't stack overflow?
Well, this is less likely, but with while you will avoid recursion on creation, but it will use recursion on deconstruction.
That's true. Okay. Fun times. What if
That's
maybe one of our tests could be getting that to happen? That'd be fun. All right. So what we need is let mute expr equals self binary
first we need to parse a unary expression, I think.
Okay, yes. So expr equals self unary or self parse unary tokens first. Okay. So first get a unary, and that's the initial value. And then at each iteration,
we need question mark and assign a new set of tokens to some variable. Parse unary gives us 2 elements.
Right. Okay. I think I need to shadow the original.
Yeah, shadow
yeah.
original tokens.
How do is there any way to do like this kind of thing
Yeah,
that works?
yeah.
Okay, very nice. So, cool.
Tokens are going to be moved as well. We will be reassigning it after each parse.
I have to think about it. This is annoying.
Next, we cannot use question mark on line 58 at the end of the expression. Just unary expression should be a valid factor. So we do let else return whatever we have.
Right, because that's the case where it's just a unary.
Yes.
And 0 iterations. Yeah, gotcha. Okay.
It's going to be let some inside mute t.
Right.
No, it doesn't have to be mute. And then else after closing, after opening paren, and here we return expression and tokens. We already have it.
Oh, yeah, you're
That's
right.
unary
Turn
expression.
some expert tokens.
Extra set of parents.
Yeah, always gets me. Okay. So now found unit type.
It's complaining about return value from this while.
Oh,
You
okay.
can add to do after they will stop complaining. Just add panic here, panic or to do.
After we get done with the while loop, we're going to do this.
Yep, that works. Extra set of parents again.
Okay. Yep.
It's not
Cool.
Haskell.
Cool. All right. So we have parsed the next token. Now we're going to put a unary. It's the right way of doing it. Let me see what his while loop is. Kind of, it feels weird it always feels weird to like set up something for the next iteration of the loop. Yeah, let's see. I guess he has a previous. Okay. While. No, okay. So while he has a thing where it's like while some current token is equal to one of these, you keep consuming. I'll do it this way and then we can sort of refactor it. So there's not this weird like assignment at the beginning. So let unary tokens equals self parse unary tokens. Oh, but it has to be tokens. Yeah. I have to do the same thing. And then
writing something, but I see the same exact people I saw in every other Rust meetup online. That's fine.
Charlie. I guess that doesn't surprise me. I only go to this one. Okay, so let t or t, which was mute here, equals tokens dot get 0. Unused variable operator, right? So I need to only use that in. Now this is weird. I think I need to structure it so that I get the operator inside the body of the loop. Why don't I just make a flag? So what? Operator matched. So now we will get an operator and then try to get another unary.
I don't think flag is going to work well. You will need, first you will need to create initial version of expression, and second you will need to update it. So here first will be creating it from the initial parse, and the rest you will be adding extra operators. With that kind of recursion, we should be able to factor it out later. But for now, we need to write one copy that works.
So are you suggesting just using recursion?
We can go to a while let.
Okay. I just don't really, I don't see how it all fits together. So, okay, you get an initial value of t. You try to get the operator. If it is invalid, then you're done parsing, so you return immediately. If it is valid, you get another unary, and then you set yourself up for testing the operator again, I guess?
I guess. Instead of using t.token, we can... no, we can't. Yeah, this looks about right.
Expert equals self binary left expert operator 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 and right unary. Okay, I think that's what he's doing. Now, why did it have trouble even saving that? All right.
I get a sum. No,
then-
tokens get 0 will give us option, and T is first it's immutable, and second it's plain variable. So you need to add mute.
Here.
You know what? Let's try to change to combine lines 59 to 61 into 62. So not only we try to parse multi-if, but before that we try to get the first item. So it's going to be, I guess I need to start the live session.
That's what I meant. Yeah, I think it's probably better if you just write what you're talking about. Does that compile? That compiles.
That compiles, but it will not produce correct result. Question mark on line 66. What? It says unable to verify something.
The live share?
Yeah. Can you try starting one more?
Okay. Okay. Share. Copy this. And we're operator matched.
Okay, so some equals. So first we tokens get 0, then T binary operator, try parse mode, try parse mode D T. I think we can do that. Call it.
Sure.
Then some. So inside of this we have operator if it exists, and it will stop processing if it doesn't exist. So from that we need.
Isn't that the same condition? What's the difference here?
It is the same condition. I can get rid of this.
I see. Okay.
And I can get rid of this. So it's just shorter.
Okay, so because we're always taking the first token, you're saying?
When it's available, yes.
Okay. Does this work?
Might need to change it a little bit to handle errors better, but for a successful case, this works.
Okay. Do I need to update Rust to get this?
With just then maybe. I'll try to remove some. Oops. Okay. Like so. Yeah, I think it's happy with this.
So, okay. Is some and? No. Then. What's then? And then?
Then it's a magnetic bind.
It's and then?
Yeah.
Okay. That sounds like what we're doing here. Okay. Compiler tucked away somewhere. How is Rust Analyzer already like struggling? All right.
Don't know, maybe it's not happy with the live session connections.
Yeah. All right, let's see if we can do a quick test for this. So okay, does the compiler also think there's an error? Yes. Simple expression. We forgot
Maybe I
curly
removed
brace
something.
somewhere. There we go. Hopefully. There we go. Okay, now it's a more reasonable compiler.
Okay, well, let's change it in the closure. That's closure. It will take something that was called T, and it's going to be T dot token. Yeah.
Okay.
My bad.
Cool. All right, let's write a quick test. And then we can wrap it up. So now we should be able to do, what did we just do? This. Oh, and by the way, this test was wrongly written last time. It should be an expression grouping.
Was it failure?
No. We also didn't write it correctly. We also just made it forget about the grouping. Yeah.
Okay.
Okay. So test parse binary. Now we want it to be expression. I'll just see what it is. I'll just see what it is. I'll let it mess up. Okay. Yes. All right.
Not implemented.
No, that's because it doesn't have a path from the top level all the way down to here. So let's just try going directly into parse factor. Still failed. Option unwrap on a none value. Where do we unwrap?
in the test.
Okay.
So something is not working.
Okay. How do I just print the tokens?
Print line.
Isn't that like
Bark.
hidden inside tests?
If test fails, it will test when it runs. It collects everything that goes to std out, std error, and if test fails, it will print everything captured.
What's the stupid format specifier?
Colon and question mark. Add after tokens, not before. We need to derive some. No, we don't. Okay.
No, Rust Analyzer is just being really slow. Okay. So we've got number, star, and then it is
And
not
that's it.
getting the 4. Very interesting. If I add a space, does it get the 4?
And now we're stuck in some recursion.
If I add a space, it does an infinite loop. All right. You have a problem. All right. Well, that is what I will be dealing with. So that's good simplification of this stuff. But yep, got some details to get straight. Okay, I'm gonna stop recording.